Okay, why don't we get started? So what I wanted to do is continue the discussion of inverters that we started last time. And what I'm going to show you is some sort of expansions on the way you can think about controlling the inverters to get better performance out of the waveforms. So we introduced the basic voltage source inverter structure, which is 4 switches. Okay, and very typically we'll use bidirectional conducting single directional blocking switches like MOSFETs, like this, for example. And if I want to synthesize some voltage Vx across the load, if I have switches S1, S2, S3, and S4, right? If I have the switches that are on be S1 and S2, I put positive VC across the load. If I put S2 and S3 on, I get 0. If I have S3, S4, I get negative VDC across the load. And if I have S4 and S1, I get 0 again, okay? And we showed last time that we can use this to synthesize, either plus 0 or minus repeatedly across the load, and then use that to at least very crudely approximate some kind of sine wave, for example. And why do I focus on a sine wave? Very often we want to synthesize something that at least if I filter it, it will look like a sine wave. Because, for example, if I'm making a UPS inverter, maybe I would like to replicate what the grid does with my inverter. Okay? And when I show this as a load, what is this? I don't know. It depends on the application, right? It could be a motor winding. It could be some low-pass filter, for example, that's going to some load, right? So this could be Vx, and this could be V out across the load, okay? So we said last time that we often think, especially when we're synthesizing periodic waveforms, we often think in terms of the Fourier series, then what we're doing to kind of shape the harmonic content of the waveforms, right? So we said, okay, one form of the Fourier series for some signal f of t is simply equal to b naught over 2 plus the summation from 1 to infinity of a sub n sine of n omega naught t plus b sub n cosine of n omega naught t, okay? Where if we recall, the sine terms are always odd in time, and the cosine terms are always even in time. So if I happen to want an odd waveform, then I should make the pattern f of t, and that means I want the pattern of f of t to be odd. That means I will only have the a sub n terms. And if I want the pattern f of t to be even, I only have the b sub n terms, okay? More importantly, we saw that we can often do interesting things with half-wave symmetry, okay? What does half-wave symmetry mean? Half-wave symmetric waveform means that f of t is equal to minus f of t minus t over 2, where t is the period. Okay, that means if I go back half of a cycle in the waveform's flipped. So for example, this waveform is both odd and half-wave symmetric. Why? Because if I go back, well, that's a terrible drawing, because this should go further, right? But if I go back at any point half a cycle, I flip across the axis and I get to the same point on the other side, okay? And the reason I'm interested in half-wave symmetry is because if it's half-wave symmetry, then the A2K and the B2K terms are 0. right? And the reason I'm interested in doing that is suppose I want to synthesize something that looks like a sine wave, and then I want to put it through a filter. It's very hard to filter out the second harmonic, right? Because second harmonic is only a factor of 2 different than the fundamental in frequency, and you know, I'm trying to use perhaps a low-pass filter. It just gets hard to attenuate that. If I can get rid of the second harmonic specifically, I can make my filtering easier. And if I can get rid of if I make it half-wave symmetric, I get rid of the second, fourth, sixth, etc., and I really reduce the amount of stuff I have to worry about filtering. So I can get much purer output waveforms by doing that. Okay, so if we're going to synthesize some pattern for my inverter to synthesize, to create, making it half-wave symmetric is significantly advantageous if I don't want any even harmonic components in my output. All right, and what we said was that, you know, if I come back to this kind of filtering, right? So if I think of the transfer function from Vx to Vo, so magnitude of Vo over Vx, right? Ideally speaking, there's going to be some kind of low-pass filter where I want to put the fundamental here, so it's in the pass band, but 2, 3, 4, 5, 6, etc. You know, I usually only want this component, and I would like to filter everything else. We can get rid of these by the half-wave symmetry, and then it's just a question of what about third and fifth and so forth, right? What we saw last time was one more trick. We said, you know, I can synthesize 0, plus, and minus. If I only switch once per cycle, I can create a waveform that looks like this. Okay, so if this is pi, this is 2 pi, this is some angle omega t, okay? If I synthesize an angle, I may have delta, pi minus delta, pi plus delta, and 2 pi minus delta, right? If I synthesized a waveform that looks something like this, and so forth, that is half-wave symmetric. So this is VDC, this is minus VDC, right? This waveform for Vx is half-wave symmetric. And the advantage I have here is I can have S4, S1, S1, S2, S2, S3, and S3, S4, and then I'm back to S4, S1. I've switched each device on and off once per cycle, and hence I've kind of got the lowest switching losses that I might get for synthesizing such a pattern. Okay, so if I care a lot about the loss in switching, which I might if I'm either at very high power where I have high voltages or very high frequencies, this is a pretty nice pattern to have. And we said my one control handle in this pattern, if I use it, is this angle delta. Okay? And by picking delta, we can do a few things. One thing we said we could do is if I make delta bigger, the fundamental component gets smaller. And if I make delta smaller, if I make delta smaller, the fundamental component gets bigger. So I can control the fundamental of the output that way. The other thing we said we could do is control the harmonics, right? Because we said if I do it like this, so for an odd waveform, right, and I'm only picking it to be odd just because it makes the Fourier series description simpler, right? But for an odd waveform, right, what I get is the nth harmonic component is simply going to be equal to, which way did I do it in terms of angle, or did I do it in terms of, I guess I did it, okay, 2 over t integral over the period of Vx of t sine of n omega t dt, okay? By picking delta, I can sort of choose at least one of these to mess with, okay? And so I can calculate the amplitude of the nth harmonic essentially as the waveform times the sine of the right frequency integrated, right? And the example I showed you last time is if I thought about what, say, suppose I focused on the third harmonic, so n is 3, right? The third harmonic would look like this. Or I'm sorry, the sine 3 omega t would look like this. And when I picked delta, this angle delta, to be exactly 30 degrees, or pi over 6. So this example is delta equals pi over 6. Okay? We notice that when I look at the intersection between Vx of t and I multiply it by the pink waveform, which is sine 3 omega t, basically I get this positive area, and then I get this negative area multiplied by the white waveform, and when I multiply them and integrate them, I get 0. Okay, so I can kind of look at this waveform and say, hey, you know, if I pick that angle just right, the overlap with this sine 3 omega t gives me just such that I kill the third harmonic. Okay? And this kind of trick we're going to see we can expand in multiple ways, okay, to give us higher performance. But before I go on, is there any question about how that arises or anything up to the present point? That's sort of the quick review of last lecture. Okay, so how might I go about it? Well, the reason I did this, a principal reason I did this was because I said, okay, I've gotten rid of the even harmonics, but I've still got to worry about 3, 5, 7, etc., right? If I picked my angle just this way, I would pin 3 to 0, right? So that would kill the third harmonic, okay? And that means, since the fourth is gone by symmetry, the lowest I have to deal with is fifth. Now I'm starting to get some nice space here, okay? And that lets me get much more pure filtered waveforms at the output compared to this kind of pulsy shape I'm generating. But what else could I do? Maybe I can play that game and get rid of more harmonics by switching more. Okay, so I've only switched each device once per cycle, but suppose I'm willing to give up on that and switch more times per cycle, on and off. That means I can sort of create more times when I have positive or 0 or negative in any given time. Okay? I would like to do that perhaps in a way that helps me get rid of some higher harmonics, right? So now that I've gotten rid of the third, my lowest are the fifth and the seventh. Maybe I could figure out some way to get rid of the fifth. Okay? Well, how could I do that? Let's think of a slightly more sophisticated pulsing waveform than the white one. Let me do this. Suppose I came and I said, you know what? If I put a 0 right here, so let me do the same thing. I will put a positive step here, but what I'm going to do is I'm going to look at this point. And if I cut out a little bit on each side of this, I don't change the fact that the third harmonic's gone, right? Because as long as I make sure the amount of positive in this multiple with the third harmonic balances the amount of negative area with the third harmonic sine wave, I will maintain 0 third harmonic. So maybe I could do something like this. I will create a pulse waveform that does this. Okay. And maybe I'll do that again on this side. Okay. And I would now want to keep my waveform half wave symmetric, so I'll do the same thing on the other side and do this. All right. Now, if I've done this in the right way and I just make this symmetric about 60 degrees, and I put it in some other angle, maybe I'll call that capital delta, right? I haven't introduced any third harmonic again, right? Because the multiple of this pink colored waveform or orangey colored waveform with this sine 3 omega t, the integral of it's still going to be 0. It's still orthogonal. Any questions about that? What do I do with delta? I can pick that when I do with capital delta here. Maybe I can pick that so the fifth harmonic goes away. All right? And in fact, I'll show you the one result, and this is just a kind of a very simple example. This is what you would get. And in this case, I'm going to pick this waveform capital delta to be exactly 12 degrees. Okay? And because my artistry is not so good, I've decided to resort to the board. I mean, to the to a figure from the book. But this is the same. You can see this is the third. This is how I cancel third harmonic. Here's sine 5 omega t. Okay, and if I multiplied this original 1 pulse per half cycle waveform by sine 5 omega t, you can see that the negative area doesn't cancel the positive area, and hence I have some fifth harmonic. Okay, but if I then put in my nulls right here, like I said, centered about 60 degrees, it turns out if I use that capital delta being 12 degrees, I can make the negative area exactly cancel the positive area and kill the fifth harmonic. So if I use this waveform, and it's again halfway symmetric, it has 3 pulses in each half cycle instead of 1 pulse in each half cycle, I could not only keep the third harmonic killed, but also kill off the fifth, which would then leave the lowest harmonic, the seventh. All right? That makes it easier for this filter to kill it, or equivalently, for the same filter, I get more pure sine wave at my actual output over here. Okay. Any questions about that? This kind of trick, where I'm going to introduce new pulses in each half cycle, is called harmonic elimination. And we can often view it as exactly through this method, as how do I synthesize pulses that sort of satisfy this orthogonality with each harmonic. Okay? Now, is this the best I can do? Well, first of all, if I synthesize this waveform, how many times do you think I switch each device per cycle? Without working it out, you can essentially, each time you get a pulse per half cycle, you have to add on some switching transitions, so you get higher switching losses, right? So what I'm really doing is I'm trading switching loss for lower filtered output components. Okay? Now, is this as good as I can do to get rid of the fifth? No, it turns out that, and you can write equations and start solving them to do this, and I've given in KPVS chapter 8, there's 2 references. There's a classic Patel and Hoft reference that introduced this general idea, and then there's a more recent Chasen reference that really goes into detail about the best ways to do this. Is each time you put in 1 pulse and a half cycle, you can ultimately pick 1 harmonic to eliminate. And when we talk about 1 harmonic, we're keeping everything half-wave symmetric, so we care about 1 odd harmonic. Okay, so we're assuming our evens are all gone. I only have odds. So I could actually pick this waveform, because I have 2 degrees of freedom, little delta in this example, gamma. I could kill the fifth and the second, fifth and the seventh, or the third and the fifth, but only have 2 pulses in a half cycle, and so have fewer switching transitions than I do in this example waveform. Okay? And generally, the rule is for each pulse per half cycle, I get to pick 1 odd harmonic to eliminate. Okay? Any questions about that?
Is there like a practical limit to how high of a harmonic you can cancel?
Yeah, that is an excellent question. There is. Because, if I want to eliminate the 97th harmonic, right, what that means is I've got to control the timing resolution just so that I, make that multiple with the 97th harmonic integrated 0, right? So the higher the number of harmonics I want to eliminate, the more precise the timing requirements become, right? So you can imagine, how would you do this? You'd have a lookup table that steps along and it says at every time slice, which switches should be on, and the number of time slices I need to break it up into accurately enough to murder those low frequency harmonics gets worse and worse and worse. The other limit is eventually I switch so many times that my switching loss goes crazy and I don't like it. Okay. The other thing I'll point out is if I took this to its logical conclusion, so suppose I came off and I said, okay, I want to get rid of a bunch of harmonics, right? So imagine my pulse waveform looked like this, and I'm just going to, I'm not going to be quantitative now, but maybe I would have something that looked like this, pulse, and another pulse, and another pulse. And these are all very controlled widths, right? And then I do this, right? Something like that, right? I don't think I have the right number of pulses here, but I have something that's shaped to generate a set of pulses that make this, at least at low frequencies when I filter it, look closer to a sine wave. Okay, maybe these middle pulses would tend to be bigger than these edge pulses. Okay? And I pick the pulsing times and positions exactly to give me this magic cancellation. What I am doing, if I think about this in the frequency domain, right, is, I've got my fundamental that I want. I've got some filter that's going to then cut off, right? And what I'm doing by doing this is I'm eliminating a bunch of the low order harmonics. But you can see that this has a bunch of high frequency content, right? I'm switching up and down and up and down and up and down. That sort of suggests to you there's a bunch of high frequency stuff there, right? So if I look at the original waveform Vx, this waveform, in fact, if I looked at its total harmonic distortion, it actually is higher. What I'm doing is I'm killing off the low frequency stuff, and then I'm really growing the high frequency stuff, right? So it's not like my waveform actually has less harmonic content. It actually has considerably more. And depending upon how you choose to, what angles you choose to kill off your low order harmonics, you will end up with more or less stuff at high frequencies. But undoubtedly, you're going to get more high frequency stuff because you've got a lot of switching going on, right? The thing about that is if I think about a low pass filter, it's easy for me to murder the high frequencies in a cutoff. It's hard for me to eliminate stuff that's near cutoff. So I'm making the challenge of basically pushing the frequency content up and kind of keeping the stuff that's hard to filter low. Okay, so I'm not sort of getting rid of high frequency content, I'm actually increasing it. But what I am is getting rid of the stuff that's hardest to filter. Okay, any questions about that? Okay, so that's one strategy I can use. What else could I do? And actually, in my original waveform here that we showed, we saw a little bit of a hint of this. And here's the idea. Suppose I have some waveform, x of t, that I might express as the summation of n equals 1 to infinity x sub n sine of n omega naught t plus phi sub n, right? It has some Fourier series. Then if I had some delayed version of this waveform, let me call this x of t minus t1, okay, what would his content look like? Well, I just go to this expression, I substitute in t minus t1, right? So I would get, okay, this is the summation of n equals 1 to infinity of x sub n sine of n omega naught t minus t1. So I'll say there's n omega naught t minus n omega naught t1 plus phi n, right? So if I define some delta phi 1, the phase shift at the fundamental associated with this time shift T1, okay, that would simply be omega naught T1. That is, if I'm shifting by a time T1, I'm shifting the fundamental by a phase omega naught T1. Okay? What am I shifting the nth harmonic by? This is the fundamental shift. Right? The nth harmonic, delta phi n, is equal to n delta phi 1. So this is the nth harmonic phase shift. Okay? And so here you can see, right, because the nth harmonic, this thing, and maybe I should be careful, define delta phi 1 as being minus omega T1, and maybe this is minus n omega delta phi 1. So this is, delta phi 1, or n delta phi 1, is the amount I'm shifting the nth harmonic. Okay, does that make sense to everybody? So why am I telling you this? Suppose I did some game like this, and I would have said that this is kind of, maybe not the most common way to play this game, but you can actually find people who've built converters this way, especially for high power. Suppose I had some DC input voltage, and I will build an inverter. Okay. Here's a first inverter, and I'll give him an output voltage, Vx1. Okay. And now let me build a second inverter, 4 switches, and I'm going to give him an output that's Vx2. And what I'll do is I'll transform or couple these two outputs like this. So, and let me just imagine this is a 1-to-1 transformer. Okay, and here's another 1-to-1 transformer. Okay, so this is Vx2. That's a 1-to-1 transformer. That means that this total Vx is simply equal to Vx1 plus Vx2, right? So I've got a first inverter generating a first pattern, and a second inverter generating a second pattern, right? So what is the content if I said that, suppose I say Vx1 is equal to the summation of n equals 1 to infinity. Let's assume I'm just doing odd waveforms of V sub n sine n omega naught t plus phi sub n, right? That means that Vx2, if I shift by T1, right? Vx2 is just going to be the summation of n equals 1 to infinity of V sub n sine n omega naught t plus n delta phi 1 plus phi n, where delta phi 1 is just equal to omega naught T1. Okay? All right. So now I have these two waveforms and I add them, right? So now I'm going to get Vx is simply equal to the summation of Vn times sine of n omega naught T1, I'm sorry, n omega naught T plus phi n plus sine n omega naught T plus phi n plus delta plus n delta phi 1. Okay? All right. Well, what happens if I make the difference between, the phase difference between this waveform and this waveform is precisely n delta phi 1. right? At each harmonic, I've got a phase shift that's, the nth harmonic is a phase shift that's n times delta phi 1. Well, what happens when n delta phi 1 is pi, or 180 degrees? What's going to happen? This is going to be 180 degrees out of this, and they're going to cancel. All right? So if I'm clever, if I go build two waveforms that are shifted in time by just the right magic amount, such that when I add them, they're 180 degrees, the harmonic that I care about is 180 degrees out of phase, it's going to cancel. Okay? This trick is called harmonic cancellation. Okay? Let's go see an example of this. So what I've done is, let's pretend I've synthesized those two waveforms, okay? And suppose the two waveforms I've synthesized with each of those bridges, each switch is switching once per cycle, so it's got a delta of 30 degrees, and I do the first guy, and then I do the second guy, but I'm shifting him by 36 degrees. I'm offsetting him by 36 degrees. What's 5 times 36? 180. So then when I shift them, then I add them, right? In the bottom waveform, you see the result here, right? And this waveform, actually, that kind of looks a lot more like a sine wave, doesn't it? Right? That's because I've canceled the fifth harmonic. In fact, not only have I canceled the fifth harmonic, I've canceled the 10th, although we didn't have 10th. I've also canceled the 15th, the 20th, the 25th, and everything. So basically, unlike harmonic elimination, where I'm playing this game by getting something that has no low frequency content but has a bunch of high frequency stuff, harmonic cancellation cancels out some waveform you care about, plus multiples of that. So it looks a lot more like a sine wave. Okay? I've now taken each of my devices, I've still only switched them once per cycle, I've just got twice as many devices that are sort of half the size to process a given amount of power. So I've sort of paid for this trick with a little bit of complexity, okay? But I get a waveform out that is very kind of much closer to pure and much easier to filter to get what you want, okay? Any questions about that as a trick? Yeah.
When you're doing this, it seems like you need to be really careful about because we actually end up at a phase inclusion on this. You know, you're in a high power situation where with your wires are heating up a bit. Did that change this? Do you have to worry about that sort of thing?
Yeah, I wouldn't worry so much about the wires heating up, but your broader point is a good one. It's just as I'm kind of limited by timing angles with this guy, how much I phase shifted, if I don't control that very well, if there's delays between the circuit, you know, depending upon how much absolute time that is, I'm limited, essentially this harmonic is limited by how accurately I control that T1, right? So I want to be very good about shifting this the right amount. Now, I will say that this kind of trick, I do need some better hardware to do it, right? I can't synthesize this level. This level is sometimes called a 3-level waveform. You say, well, there's not 3 levels here, but the way they count it is 1/2 of this waveform is, you know, 0 plus VDC over 2 and plus VDC. You know, one polar side has 3 levels. So they call that a 3-level waveform. With a 3-level waveform, I can choose to cancel a harmonic, right? Now, what we'll see later is sometimes I might choose the 3rd, sometimes I might choose the 5th. It depends on what I'm doing. And in fact, even if you come back to this original waveform that I drew, right, this waveform, the original white waveform that had those 30-degree shifts, what I could really view that is 1/2 of this bridge generating a square wave, and the other half of the bridge generating a square wave that's 60 degrees out of phase at the fundamental and sends at 3 times the frequency at the third harmonic, or 6th, 9th, 12th, etc., it'll be 180 degrees out of phase. So in fact, the pulse waveform, the one pulse per cycle waveform that I showed you, you could really view it as a cancellation because I have 2 half bridges that are each generating square waves, and I get a harmonic cancellation between those square waves, killing the triple N harmonics. But yes, as I go up in frequency, it becomes harder to do, and I need fancier circuitry to cancel lots and lots of harmonics, but sometimes it's worth it. And people, as we'll see, people actually do quite fancy circuits to help them do that. Other questions?
In this example, the third harmonic is still canceled because of the two shaping first to it.
Yeah, exactly. That's the beautiful thing about this, is once I've canceled the waveform, and then I take some cancellation, then I add it to some other waveform, I can't introduce new harmonics, right? I'm just taking some existing set of Fourier coefficients. The most that can happen is they sort of add up and stay constant, right? In other words, if I take 2 half-size waveforms and add them up, the most I'm going to get is back to the original. Other than that, I'm just going to get some degree of cancellation. So I don't introduce new frequencies by doing this trick. I just kill frequencies. So yes, so my original white waveform, because it's sort of harmonic cancellation of the 2 half bridges, I have no triple N harmonics, no 3, 6, 9, 12, 15, 18, and so forth, right? I don't have any evens because of the half-wave symmetry. And then if I do this trick, I kill off all the 5N harmonics. And you can keep that game up. If I had a more complicated circuit, I'd kill even more. And the waveform just becomes, you know, it starts to become very small, steppy, close to a sine wave, and you get very beautiful waveforms. Okay. Yeah.
Does the 6-degree displacement matter?
Does the which?
Because it's a sine wave, but it's displaced by 6 degrees. So
it's a way. Oh, yeah. Okay. So actually, if you look in the lecture notes, instead of displacing it by 36 degrees, I displace one by plus 18 and one by minus 18, and you get the same cancellation, and then it stays odd. Yeah. So I don't have to have 0 plus a delayed. I can have minus half the delay and plus half the delay, and it still stays as an odd waveform. Excellent question.
Sir, do you also use this trick to just like increase the AC output voltage?
You could, yeah. So yeah, what would be another benefit of this? Right, the Vx has twice the amplitude of VDC I could synthesize. Another way, and that's just for this particular implementation, which is only one way to do it. We will see next class other circuits that their benefit is they use, for a given input voltage, they use lower voltage switches to get the same output. So there's a lot of ways you can, you know, take advantage of the complexity you inherit. The downside to this one is principally that I have transformers that are rated for the output, that are rated for the frequency I'm outputting. You know, in some cases I might not like that, but there's other circuits that get around that. Let me point out that this notion, this cancellation notion, is a very widespread one. It gets used in a lot of kinds of circuits. Let me show you another one that maybe is completely different application space. But suppose I had a buck converter, okay, that looked like this. Okay. And here's my output capacitor. Okay, and here's my load. And maybe this output capacitor is a microprocessor. So maybe this is the 12 volts input, and I'm delivering voltage to my microprocessor, right? This current here is a triangle wave, right? So maybe this current looks something like this. It's got some DC value, and it's got some ripple. Okay, at the switching frequency. maybe if I came in with a second unit, all right, and I will build another parallel guy here, and I will switch him with some phase shift, and he'll have an output current. And maybe I make this output current, you know, here's T over 2, okay? And here's, gotta be careful, here's 3T over 2. Here's 2T, right? Maybe I will shift this one so that he starts half a cycle later, like this. Okay. What total current goes into the output and capacitor? Well, it's the sum of this one and this one. But if I basically make orange and pink shifted by 180 degrees of the fundamental, that means the fundamental ripple will cancel. If there's second harmonic component in the pink waveform, the second harmonic of the orange waveform will be shifted by 360 degrees at the second harmonic. So the fundamentals will cancel, the second harmonics will reinforce, and the net ripple, I'm not even going to try to draw it here, but it would basically have a fundamental that was at twice the switching frequency, right? So I get something that's both smaller amplitude, and you can show that the amplitude will be at most half, and twice the frequency, which makes it 4 times as easy for that capacitor to filter it. All right? So this same kind of trick of harmonic cancellation, here I'm canceling the fundamentals because what I would like is a DC output current. This technique is called interleaving. It's very widely used, and in fact, most motherboards, if you look at them, they don't have a buck converter or something driving the load. They'll have a whole bunch of buck converters lined up, and they phase shift them all just such that the first N harmonics will go away, and the ripple frequency will be much higher than the switching frequency of the individual converters. That also means that you can play with response speeds of that, because one will react, you know, sort of much quicker than if they were all in phase. If I put these two converters in phase, all I would get is twice the ripple current at the fundamental. Instead, I get at most half at twice the frequency, right? And I can play that game out to N different converters interleaved. So this trick of harmonic cancellation is really neat. It's widely used. It's used in DC-DC converters. It's also used to kill off unwanted harmonics in inverters. Harmonic elimination is also used. There's nothing that says you couldn't do the two of those together. You sort of saw that, right? Instead of using that just one pulse per half cycle, I could use some pulses per half cycle to eliminate some harmonics, use some phase shift, and eliminate some more, and I can intermix those two, and they get very nicely, easily filtered waveforms. Any questions about that? Okay, just to demonstrate all this, Rafa has been kind enough to set up a demo, so I'll let her show you some actual experimental waveforms from an inverter that was built by a student who took this class.
Okay, so what are we looking at? Am I too loud? Sorry. What are we looking at the top is, guess what? What inverter is it? So I have an inverter board that has 4 switches, and we're probing at the output voltage. So we had a DC input voltage of 15 volt, and then we're switching it. And as you can see, as we saw in class, it uses the 3 levels, 0, positive, negative, to create something that somehow resembles a sinusoid. And as you can see, it has half-wave symmetry, so we do not have any A2K, B2K, or the even harmonics. So we only have to worry about the odd harmonics. Now let's, at the bottom down here, we are looking at the FFT of the voltage waveform. So the voltage magnitudes at different harmonics. Now, if I move my cursor at the first spike where it happens, it's really hard to see, but you can see on the top right that it's happening at 600 Hertz, which means that's our switching frequency, and it's the fundamental. And then let's see where the next spike happens, the second highest spike happens at 2.9 kilohertz, which is very close to the fifth harmonic. What does that mean? That means we do not have any third harmonic. So we eliminated the third harmonic from the circuit. Now, let's do another thing. It's going crazy, but let's see. Okay, now, like we saw in the class, if we introduce pulse or notches on both sides of the waveform, it's still half-wave symmetric. So we're still doing the same thing, but interestingly, if we move to the second high spike, it's almost about 4.2 kilohertz, which is the seventh harmonic. So we eliminated third and fifth harmonic. Now we can take this a step further. Let me run it and stop it. Okay. Yes, so now if we move all the way back, that will be the second spike occurs at 5.3 kilohertz, which is like the ninth harmonics. So we eliminated all the lower third, fifth, seventh harmonics. You will notice that they're getting a bit, so the higher harmonics are getting higher in magnitude, but that's okay because we care about the lower harmonics more, because it's easier to get rid of the higher harmonics. We'll need smaller filter components or smaller devices for applications. That's all.
Thanks. So I guess what we've seen today is harmonic elimination, where we introduce extra pulses carefully timed. We've also seen harmonic cancellation, where we take multiple waveforms and shift them and add them up to kind of murder the harmonics we don't like. Those can be both used together. What we'll start seeing next time is, firstly, well, other ways we can do this kind of harmonic cancellation or harmonic elimination game, more sophisticated circuits. And after that, we'll start talking about, well, what happens if, we've kind of posited this on the whole thing I want to make as a sine wave, which is often true. If I'm going to run a lot of kind of motors, I want a sine wave. If I'm trying to generate, something for the AC grid, which is supposed to be sinusoidal, I want a sine wave. But there's times we don't want a sine wave. So what do we do in those cases? And we'll pick those topics up next class. So have a great day.